All right, so picture this. 1821, London. A machinist named Henry Maudslay is standing in his workshop staring at a box of screws. Not just any screws, mind you, but screws he'd personally made in his own shop. And here's the thing that's driving him absolutely mad. None of them fit each other. Not a single one. Same shop, same machines, same year, but grab a nut from one batch and a bolt from another? Nothing. Just wouldn't thread together. And Maudslay wasn't some amateur, you know? This was one of the finest precision engineers in all of Britain, the man who'd built some of the most accurate lathes in the world, and even he couldn't make two screws that would reliably work together. Now, you might be thinking, well, how hard could it possibly be to make a screw, right? It's just a twisted piece of metal, spiral some threads around a shaft, call it a day. Except, no, not even close. Because what Maudslay had stumbled into wasn't just a workshop problem. It was a crisis that had been brewing for literally thousands of years. A problem so fundamental, so maddeningly complex, that it would take humanity another half-century just to begin solving it. See, the screw itself is ancient, really ancient. We're talking around 200 BC when a Greek mathematician named Archimedes supposedly invented what we now call the Archimedean screw. Though honestly, he probably didn't invent it. He likely just described something that already existed. This was a large screw mechanism used for lifting water, rotating inside a cylinder, pulling water upward as it turned. Brilliant piece of engineering. Farmers used versions of this thing for irrigation for centuries. But here's where it gets interesting. That wasn't actually a fastener, was it? It was a water pump. The screw as a way to hold things together, to clamp metal to metal or wood to wood, that came later, much later. And when it did show up, it showed up everywhere, all at once, in dozens of different forms, and absolutely nobody could agree on how to make one properly. By the 1500s, you start seeing screws used in armor, in clocks, in scientific instruments. Craftsmen would hand file threads onto bolts, one at a time, matching each bolt to its specific nut. You couldn't just swap parts around. Each screw was married to its nut for life. Lose one, you made a new pair from scratch. And I mean from scratch, no templates, no standards. Just eyeball it and hope. Fast forward to the 1800s and things aren't much better. The Industrial Revolution is starting to kick into gear, literally, and suddenly you've got factories trying to mass-produce machinery, steam engines, textile mills, printing presses, all of it held together with screws that were made by hand, one by one, by individual workers who each had their own idea of what a proper thread should look like. You'd have a machine built in Manchester with parts that couldn't be replaced by anything made in Birmingham. Even within the same factory, screws from different workbenches wouldn't fit together. It was chaos, absolute chaos, and it was costing manufacturers a fortune in wasted time and material. Because here's the thing about screws that nobody really thinks about. They're not just fasteners, they're mechanical translators. They convert rotational motion into linear force. That's why they can clamp things together so tightly. That's why they can lift enormous weights with relatively little effort. But that conversion depends entirely on the geometry of the thread. The angle, the pitch, the depth. Change any one of those variables, even slightly, and suddenly your screw doesn't work the same way, or doesn't work at all. And in the early 1800s, every single machinist had a different opinion on what those variables should be. Some liked steep thread angles, some liked shallow, some spaced their threads close together, some spread them out. There were V-threads, square threads, buttress threads, acme threads, regional variations, national variations, workshop variations. It was like the Tower of Babel, except instead of languages, it was screws, threads. So when Henry Maudslay stood there in 1821 staring at his box of incompatible screws, he wasn't just annoyed. He was staring at the single biggest unsolved problem in industrial manufacturing, a problem that was about to get a whole lot worse before it got better. Because across the English Channel and across the Atlantic, other engineers were running into the exact same wall, and some of them were about to decide they'd had enough.
So,
1834 rolls around, and there's this young engineer named Joseph Whitworth who's working in Maudslay's shop. 29 years old, sharp, obsessive, the kind of guy who measures things to the 10,000th of an inch just because he can. And he's watching this whole screw situation unfold day after day, and it's driving him up the wall. Now, Whitworth had come up through the best workshops in England, worked for Maudslay, worked for Joseph Clement, who was building Charles Babbage's difference engine at the time. He knew precision. He understood mechanical tolerances better than just about anyone alive. And what he saw when he looked at the screw problem wasn't just inconvenience. He saw opportunity. See, by the 1830s, Britain was the industrial powerhouse of the world, right? Factories everywhere, railways spreading across the countryside like iron spider webs, and every single locomotive, every piece of rolling stock, every rail junction was held together with thousands of screws. Screws that didn't interchange, screws that had to be custom fitted, screws that when they broke couldn't be replaced without custom manufacturing a new one. The railway companies were losing their minds over this. You'd have a locomotive break down in, say, York. Simple problem, one broken bolt on the valve gear. Should be a 10-minute fix, right? Except the only replacement bolts are back in the workshop in London, and they're custom made for that specific engine. So now your locomotive is sitting dead on the tracks for 3 days while someone hand makes a new bolt and ships north. Multiply that across thousands of engines, tens of thousands of parts, and you start to see the scope of the disaster. Britain's industrial might was being strangled by the humble screw. So, Whitworth decides he's going to fix it, just fix the entire problem, single-handedly if necessary. And in 1841, he presents a paper to the Institution of Civil Engineers in London. Title? A uniform system of screw threads. Not catchy, I'll grant, but revolutionary. What Whitworth proposed was deceptively simple. One standard thread angle, 55 degrees. One standard pitch series, based on the diameter of the bolt. Rounded roots and crests on the threads instead of sharp corners. And, crucially, a complete table of dimensions that any machinist anywhere in Britain could follow. The 55-degree angle wasn't random, by the way. Whitworth had tested it. He'd measured the strength of threads at different angles, measured how they wore over time, measured how much force they could withstand before stripping. 55 degrees gave the best balance of strength, durability, and ease of manufacturing. The rounded thread form was even smarter. Sharp corners concentrate stress. They're also harder to cut accurately. Round them off, and suddenly your threads are stronger and easier to make. Basic physics, really, but nobody had bothered to prove it systematically before Whitworth did. Now, you'd think the engineering community would have jumped on this immediately, right? Finally, someone solved the problem. Let's all switch over and get on with our lives. Yeah, no, not even close, because Whitworth's system threatened something more important than efficiency or safety or even money. It threatened pride. British machinists had been making screws their own way for generations. Their fathers had taught them, their grandfathers had taught their fathers, and now some upstart from Manchester was telling them they'd been doing it wrong the whole time. You can imagine how well that went over. Plus, retooling was expensive. Every lathe, every tap and die set, every threading machine in every workshop across the country would need to be replaced or modified. We're talking tens of thousands of pounds, maybe hundreds of thousands. Who was going to pay for that? So adoption was slow, painfully slow. Through the 1840s and 50s, you'd have some companies using Whitworth screws, some sticking with their own systems, some using a bit of both just to make things extra confusing. The railway companies started pushing for it, which helped. The British government started using it for military contracts, which helped more. But then the Americans got involved, and that's when things got really interesting, because across the Atlantic, American engineers were watching Whitworth's work with great interest, and they decided they could do better. See, the American manufacturing system was evolving differently than Britain's. The Americans had this concept they called interchangeable parts, pioneered by guys like Eli Whitney and Samuel Colt. The idea was that you could make components so precisely that any part could replace any other part without custom fitting. Revolutionary stuff, and screws were a huge part of making that system work. But Whitworth's 55-degree angle, the Americans thought it was overly complicated, too hard to measure accurately, too easy to get wrong. And those rounded threads? Sure, they were strong, but they were also harder to inspect visually. You couldn't just look at a Whitworth thread and see if it was cut correctly. So, in 1864, an American engineer named William Sellers stands up at the Franklin Institute in Philadelphia and proposes his own system, the United States Standard Thread, later called the Sellers thread. 60-degree angle, flat-topped threads, flat-rooted threads, simpler to measure, easier to manufacture, and, in Sellers' opinion, just as strong as Whitworth's. Now we've got a problem. Two competing standards, both claiming to be the right way to make a screw, both backed by powerful industrial interests, both used in thousands of factories and workshops, and absolutely no way to make them compatible with each other. The Great Screw Thread War had officially begun.
All right, so now it's the 1870s, and the screw thread situation has gone from annoying to genuinely dangerous. And I mean that literally. Ships are sinking, bridges are failing, factory equipment is tearing itself apart, all because nobody can agree on how to cut a stupid thread. Let me give you an example. 1873, the HMS Captain, a British Royal Navy warship, capsizes off Cape Finisterre. 573 men drowned. Now, the official inquiry blamed the ship's design, which, fair enough, it was top-heavy, but buried in the engineering reports was something else. The ship's stability systems, the machinery that was supposed to keep it upright, had multiple components that wouldn't fit together properly because they'd been built in different dockyards using different thread standards. Could they have fixed it? Sure, with custom fitting and hand-filed adjustments, but that takes time, and ship captains have schedules to keep, and, well, corners got cut, and 500 men paid the price. This kind of thing was happening everywhere. Not always as dramatically, but constantly. A textile mill in Massachusetts buys replacement parts from a supplier in Connecticut. The threads don't quite match. The bolts work, kind of, but they're loose. 2 months later, a drive shaft comes apart at full speed and 3 workers are injured. Whose fault is it? The manufacturers, the suppliers, the mill owners? Nobody knows, because there's no standard to point to and say, this is what it should be. The insurance companies are going crazy. The courts are backed up with lawsuits, and engineers on both sides of the Atlantic are screaming for someone, anyone, to take charge and fix this mess. But here's the thing. Whitworth's system and Sellers' system weren't just technically different. They represented fundamentally different philosophies of manufacturing. The British system was about precision, tight tolerances, perfect fits. The theory was that if you made your parts exactly right, they'd last forever and never fail. The American system was about practicality, good enough tolerances, easy inspection. The theory was that parts would wear out eventually anyway, so why break your back trying to make them perfect? Make them good enough to work, easy enough to replace, and cheap enough to throw away when they wear out. And, both approaches had merit. British machinery was built like Victorian architecture, over-engineered, solid, meant to last generations. American machinery was built like America, fast, efficient, replaceable. Different values, different industrial cultures. But now, these two systems were colliding because international trade was exploding. American locomotives were being sold to British colonies, British ships were being fitted with American engines, and nothing fit. Physically, mechanically, nothing fit. The International Standards Congress in 1879 tried to mediate. They got together in Paris, engineers from a dozen countries, and tried to hammer out a compromise. Maybe average the two systems, use Whitworth's angle but Sellers' flat threads, or Sellers' angle with Whitworth's rounded threads. Yeah, that went about as well as you'd expect. The The British delegation walked out. The Americans refused to budge. The French proposed their own system, which nobody took seriously. The Germans said they'd think about it. Complete disaster. And through all of this, actual working engineers were stuck in the middle. Imagine being a machinist in, say, 1880. You've got a machine shop, you need to carry tap and die sets for Whitworth threads because some of your customers need them, but you also need seller's threads for other customers. Oh, and some of your older equipment still uses the old British standard threads that predated Whitworth, and French gas pipe threads, and German metric threads, and Italian threads, and your tool cabinet looks like the United Nations of fasteners, and every single project requires you to stop and figure out which system the customer wants, which system the parts you're working with actually use, and which taps and dies you'll need to dig out of storage. It gets worse. By the 1880s, the railways are expanding globally. The British are building railways in India using Whitworth threads. The Americans are building railways in South America using sellers threads. And when these systems eventually connect, when trade routes merge and locomotives need to cross from one network to another, the maintenance crews discover they need 2 complete sets of tools, 2 complete inventories of spare parts, double the warehouse space, double the cost, double the confusion. Some companies tried making adapters, special nuts that were threaded Whitworth on one side and sellers on the other. And you know what happens? The adapter becomes the weak point. It strips under load, or it cross-threads, or it loosens up from vibration. You're adding complexity to solve a problem that shouldn't exist in the first place. Meanwhile, and this is the really frustrating part, the actual mechanical differences between the two systems, we're talking about 5 degrees of thread angle, a few thousandths of an inch in pitch diameter. If everyone had just agreed on one system, either system, it wouldn't have mattered which one it was. The benefits of standardization would have far outweighed any technical advantages one system had over the other. But that's not how humans work, is it? National pride, corporate interests, patents, ego, all of it getting in the way of basic common sense. And then came the World Wars, both of them, and suddenly the screw thread problem stopped being an inconvenience and became a matter of national survival.
So World War I breaks out in 1914, and within months, the screw thread problem goes from annoying industrial quirk to full-blown military crisis. Because now you've got the British and French trying to supply each other with weapons, ammunition, vehicles, all of it. And guess what? The threads don't match. French artillery pieces can't use British replacement parts. British aircraft engines can't accept French fittings. And we're not talking about minor inconveniences here. We're talking about soldiers in trenches waiting for supplies that don't fit. Aircraft grounded because a replacement bolt won't thread into the engine mount. Artillery batteries sitting silent because the recoil mechanism needs a part that physically cannot be manufactured to fit both British and French standards simultaneously. The Americans joined the war in 1917, and they bring their sellers threads with them. So now you've got 3 major allies, each using different screw standards, trying to fight a coordinated war. The logistics officers were having nervous breakdowns. Field repair shops near the Western Front literally had to maintain separate inventories for British equipment, French equipment, and American equipment. And the weight of those redundant parts, the shipping space, the warehouse requirements, all of it was eating up resources that could have been used for actual ammunition or food or medicine. Some engineer in a supply depot somewhere calculated, this is probably apocryphal, but supposedly calculated that the British and French forces combined were carrying an extra 2,000 tons of redundant fasteners just so they could maintain equipment from both countries. 2,000 tons. That's the weight of 10 fully loaded Lancaster bombers, just in screws that existed only because nobody could agree on a thread angle. After the war ended, there was this brief window where everyone thought, okay, surely now we'll fix this. We just fought the war to end all wars, millions dead, economies in ruins, and part of the reason it was so expensive and complicated was because our screws didn't fit together. Surely that's motivation enough to standardize. Nope. The League of Nations tried, the International Standards Association tried, engineers from every major industrial nation got together multiple times through the 1920s and 30s, and every single time they couldn't reach agreement. The British wouldn't abandon Whitworth, the Americans wouldn't abandon sellers. The Germans had their own system by now, the Soviets were developing something different.
And then, because apparently we didn't learn enough the first time, World War II starts in 1939, and the same problems come roaring back, except worse, because now you've got even more countries involved, even more equipment being shipped across even longer distances, even more languages and currencies and manufacturing standards all colliding in real time. The Americans and British are allies again, which is good, but their equipment still doesn't fit together, which is bad. American Sherman tanks supplied to Britain under Lend-Lease need British repair depots to stock completely separate parts inventories. British Spitfires being maintained by American ground crews in North Africa need adapters and custom fittings. It's madness. And here's where it gets interesting. The Germans, for all their faults, had figured something out. They'd pushed hard for metric standardization across their military and industrial base before the war. Not perfectly, they still had legacy equipment with odd threads, but better than the Allies, and that gave them a real, measurable advantage in logistics and field maintenance. The Soviets, same thing. They'd gone metric in the 1920s, mostly by just copying German standards after the Treaty of Rapallo, and while Soviet quality control was, let's say, variable, their parts at least theoretically fit together across their entire industrial system. So by 1945, when the war finally ends, British and American planners are sitting on mountains of after-action reports, and buried in all those reports is a recurring theme. We lost time, we lost equipment, we probably lost lives because our threads didn't match. And this time, finally, people listen. The British Standards Institution and the American Standards Association start talking seriously in 1946. The goal is to create a unified standard that both countries can adopt, something that splits the difference between Whitworth and Sellers, or maybe just picks one and convinces the other side to swallow their pride and switch over. This process takes 2 years, 2 full years of negotiations, testing, arguing, compromising. And in 1948, they unveil the Unified Thread Standard, later called UTS. 60-degree thread angle, like Sellers, but with specific radius requirements for the thread roots, a nod to Whitworth's strength testing, a hybrid, a compromise that nobody loved but everyone could live with. The British agree to phase out Whitworth threads for new equipment. The Americans agree to adopt the unified standard across their military and aerospace industries. NATO, which is just forming, agrees to make it mandatory for all member nations. Finally, after more than a century of chaos, 2 of the world's major industrial powers are using the same screw threads. But that only solves half the problem, because the rest of the world still doing their own thing. The Soviets have their own metric system, the Chinese have their own standards, India's using leftover British Whitworth threads, Japan's using a mix of metric and proprietary systems. The international screw thread situation is still a disaster, just a slightly more organized disaster. And that's where the International Organization for Standardization comes in, ISO, founded in 1947 specifically to solve problems like this. And in 1965, they publish ISO 68, the first true international metric screw thread standard. Will the Americans adopt it? Well, we'll get to that.
So here's where the story gets, well, complicated isn't even the right word. It gets American. Because while the rest of the world spent the 1960s and 70s slowly, grudgingly shifting toward ISO metric threads, the United States dug in its heels and said, nah, we're good. And to be fair, you can kind of understand why. By the 1970s, the entire American industrial base was built around imperial measurements and unified threads. Every factory, every machine shop, every warehouse full of parts. Converting to metric would cost billions, maybe tens of billions. Who's going to pay for that? Congress actually tried in 1975, the Metric Conversion Act. The idea was to gradually transition the country to metric over 10 years. Make it voluntary at first, then mandatory. And, yeah, that didn't work. The automotive industry pushed back. The aerospace industry pushed back. The construction industry pushed back. Everyone pushed back. Because retooling is expensive, and expensive is bad for quarterly earnings. But here's the thing. While America was refusing to convert, the rest of the world was moving on. European manufacturers went metric. Asian manufacturers went metric. South American manufacturers went metric.
And American companies that wanted to sell products internationally suddenly found themselves in the same position British companies were back in the 1800s. 2 sets of tools, 2 sets of inventory, 2 sets of engineering drawings. Double the complexity, double the cost. The automotive industry got hit hardest. In the 1980s, you'd have American car companies building engines with some parts in imperial threads and some parts in metric threads, because some components were made domestically and some were imported. Mechanics hated it. You'd be working on a Ford, let's say, and you'd need both a metric socket set and an imperial socket set to remove different bolts on the same engine. And if you grabbed the wrong wrench and rounded off a bolt head, well, congratulations, you just turned a 5-minute job into an hour-long nightmare involving drill bits and extractors. NASA learned this lesson in 1999. The Mars Climate Orbiter, a $325 million spacecraft, slammed into Mars and disintegrated because one engineering team at Lockheed Martin was using imperial units and another team at NASA's Jet Propulsion Laboratory was using metric. The navigation software got confused. The spacecraft's orbit was wrong by about 100 kilometers, and $325 million became a very expensive cloud of metallic vapor in the Martian atmosphere. And the cause? Unit conversion error, which at its core is the same problem as non-standardized screws. Different groups using different systems, assuming everyone else is using the same system they are, and nobody checking until it's too late. So, gradually, quietly, American industry started converting. Not because Congress mandated it, not because of any grand plan, just because it was becoming too expensive and too dangerous not to. Modern American cars are almost entirely metric now. Military equipment is mostly metric, consumer electronics, metric, medical devices, metric. Aerospace is split because old American aircraft with imperial threads are still flying and still need parts, but new designs are metric. And today, in 2025, we live in this weird hybrid world where ISO metric threads are the global standard, but imperial threads haven't gone away. They're legacy, maintenance threads, the threads you need when you're repairing something built 40 years ago. Every modern machine shop stocks both types because both types still exist in service. But here's what's remarkable. The actual number of thread standards in common use has collapsed. In the 1800s, there were literally dozens, maybe hundreds of proprietary thread systems. Every major manufacturer had their own. Today, there's basically 3. ISO metric, which is used almost everywhere, Unified Thread Standard, which is the American Imperial System and its variants, and NPT, National Pipe Thread, which is used specifically for pipe fittings and somehow persists despite being objectively terrible at what it does, but that's a rant for another time. 3 standards, down from hundreds, and those 3 are well documented, well regulated, and genuinely interchangeable. If you buy an M8 bolt in Japan and a nut in Germany, they'll fit together perfectly. Every time. That wasn't possible 150 years ago. The screw thread wars are over. We won. Humanity won. And the victory is so complete, so total, that most people don't even realize there was ever a war to begin with. You go to a hardware store, you buy a bolt, you screw it into a threaded hole, and it just works. That's magic. That's the result of more than a century of arguments and compromises and international treaties and engineering standards committees arguing about thread angles. And the result? Modern manufacturing is possible. International supply chains are possible. You can design a product in California, make parts for it in China and Germany and Mexico, and assemble it in Texas, and all the screws fit together. First try, every time. Because we finally agreed on how to make threads. That's the legacy of Joseph Whitworth staring at his box of incompatible screws in 1821. That's the payoff from William Sellers arguing for simplicity in 1664. That's what came from soldiers in 2 world wars discovering that logistics matters as much as courage. So, next time you're working on your car or assembling furniture or fixing a broken appliance, take a second to appreciate the humble screw, because that little piece of threaded metal represents one of humanity's greatest and most hard-won achievements. We learned to cooperate internationally across languages and cultures and competing economic systems. We agreed on something, And because we did, the modern world works. Not bad for something invented to lift water out of the ground 2,000 years ago.